Okay, so welcome back to class. The plan for today is to finish up 8.3, cover 8.4. That'll wrap up chapter 8 on solving linear equations, and then do a quick chapter 8 review. Um, that will bring us to the end of class today. This coming week, or next week, however you want to say it, is Thanksgiving break, so no class meetings next week. But when we come back, we have quite the flurry of activity. Again, as I mentioned before, Thanksgiving break is quite late this year. It's Thanksgiving is as late as it can possibly be, which really brings us to a pretty significant crunch at the end of the semester. We only have 1 week when we come back, and in that week, we're going to be squeezing in a discussion of Chapter 9, the Unit 3 exam during that week, and then we jump right into finals week with the final exam. The final will be available from Friday the 6th through Friday the 13th. So if you do plan to take the final exam that Friday or over the weekend, if weekends work better for you, there's a lot going on this week. You certainly can push the final exam to finals week. That's perfectly okay. I just open it up a little early because I know that in these remote sections, flexibility is, often the reason that folks opt for this type of section, and the weekend, might give you a little more flexibility there. The final exam is comprehensive. It's chapters 1 through 9. And the Unit 3 exam will be on sections 5, 6, and 5, 7, and chapters 6 through 8. So basically the material that we left off with after Unit 2 exam through the material that we're covering today. So over break, or probably in the next day or so, I will have a sample Unit 3 exam posted, once we finish up our work today and I know exactly what we got through. Planning to get through all of this today. I don't think we should have a problem with that, but I always do like to wait until after I cover the material to make the exam. So then we'll have the Unit 3 exam, sample exam posted. And I'll try to have the sample final exam posted sometime over break, so you can start kind of prepping for that a little bit early as well. And like I mentioned, I would kind of recommend, because Thanksgiving break is so late, not taking just the entire week off and completely forgetting about school, but maybe taking a couple of days over Thanksgiving break and doing a bit of schoolwork. So less intense than maybe a normal week, but continuing to touch base with the material, working ahead a little bit, maybe getting caught up a little bit in other areas, and that'll make the last couple weeks go much more smoothly. And then once you hit, finals week and you finish all your finals and projects and papers and everything submitted, then kick back and you can kind of brain dump. You can forget about school at that point for the next month or so. And the quote of the day today, I can't remember if I had used this one already in the semester or not, but I think going into the holidays, it is always a good reminder. The concept of always being reachable makes us present nowhere. So, sometimes during the holidays, it's nice to disconnect and be a little more present with the folks that you're physically present with, and kind of avoid some of those distractions which are so tempting with, the cell phone constantly buzzing or beeping, or coming up with pop-ups that are absolutely urgent and need your attention right now. And you know but somehow, all of these kind of things were able to wait 20 or 30 years ago. So just focusing on what is actually important, and not these kind of false senses of urgency we tend to get these days. Okay, so moving on to 8.3, we talked last time quite a bit about solving linear equations with variables and constants on both sides. And we said the general strategy looks something like this. We start by simplifying. We simplify the left and the right-hand sides individually to get to a form that looks like ax plus b equals cx plus d. So number times x plus number on both sides. Now, we might end up with, explicitly seeing number times x plus number on both sides, or we might end up with, say, ax equals cx plus d or something like that. Maybe b is 0 in some cases, but we shouldn't have anything more complicated than this. And then our goal is to isolate the variable term to get something like ex equals f. And we typically do that in two steps. We get the variable terms together on one side. It doesn't much matter which side we choose, but I tend to choose the side that will make the coefficient of the variable positive. Just a little easier to work with that way. And that also makes some future material a little bit easier as well. So when you get into O90 and we're dealing with, say, linear inequalities, it makes that solving those a little easier. And then we isolate the variable itself by dividing by the coefficient. Oh, I think I left out a step when I was describing it. We want to get the variable terms together on one side, and then we want to move the constants to the other side to get, say, ex equals f. And then we divide by the coefficient to isolate the variable itself to get the answer. And then we check by substituting back into the original equation. If all went well in steps 1 through 3, we should have the answer without any problem. But we do the check just to make sure that if we made a mistake along the way, that way we'll catch it. As a side note, so in theory, the check here is not necessary. It's really just a check on our work if we made a mistake or not. But there are other scenarios in future courses where the check is really absolutely crucial. So it is good to get in the habit of checking your work, not just for checking your work in case you made an error, but also because in future types of equations that we'll run into in future courses, not in this course, it's crucial to check because you might end up with a solution that you think is a solution that ends up not being a solution. Not because you did any work wrong, but just because of the nature of that type of problem. So getting in the habit of checking at the end is a good habit to get into. And I know it sounds a little bit hypocritical because I often don't check our work in the lectures. That's mainly because I think it's a better use of our lecture time for me to show you more examples of more different problems being solved than to show you a bunch of examples of me plugging back in and doing all of the arithmetic to check the work. That's material that we should be pretty comfortable with at this point. But when you're going through your notes, going back every once in a while and checking an answer is probably a good idea. And when you're doing your homework, always wrapping up with checking the answer, again, probably a good idea. And on the exam, same kind of thing. If you're a little bit worried about time on your exam, you can go in you can go through, answer all your questions. If you're running out of time at the end, then enter your answers and finalize them and cross your fingers. But if you have extra time at the end, then go back and check your solutions, especially for the more complicated ones, the ones that had more equation solving steps. Go back and plug your answers in and check them and verify that that is the correct answer before finalizing things. So all right, so moving on, we're continuing with section 8.3 that we were working with last time, but we're now working with more challenging problems where the left and right sides look a little bit more complicated and require a bit more simplification on the front end. So let's look at this one. Solve 5 times 2x minus 1 plus 7 equals 2 times x plus 3 plus 10x. So the first thing we're going to do is simplify. We're going to take our left-hand side, 5 times 2x minus 1 plus 7, and work to simplify this. We want this to look like ax plus b. No more complicated than that. I do notice that I can distribute the 5. 5 times 2x gives me 10x. And 5 times 1 gives me a minus 5 plus 7. And I notice that I have some like terms here. My constant terms can add together. Negative 5 plus 7 gives me plus 2. So my left side simplifies down to just 10x plus 2. That looks like ax plus b. I'm happy with that. What about my right side? Something pretty similar. 2 times x plus 3 plus 10x. Again, I will distribute. I get 2x plus 2 times 3 is 6, plus 10x. And I can use my commutative property of addition to swap the 6 and the 10x, and the 2x plus 10x gives me 12x plus 6. That also looks like ax plus b, or cx plus d, I suppose. So we're happy with that. That is simplified. So now I'm looking to solve the equation 10x plus 2 equals 12x plus 6. This is a much nicer equation to solve than the original one with all these parentheses and things in it. Okay, I've completed step 1. I now want to isolate the variable term, and I'll do that in 2 sub-steps. I'll get the variables on the same side so that I only have one variable term showing up in my equation. Right now, I look at my equation as a whole and I see x popping up in 2 different places. I want it to only be in one place. I could move the 10x to the right side or the 12x to the left side. But if I move the 10x to the right side by subtracting 10x off of both sides, right, I have a 10x on the left. I can add the arithmetic inverse. I can add negative 10x. And then 10x minus 10x will be 0. That gets the 10x off the left side. That gives me 2. And 12x minus 10x gives me positive 2x. So as I said, I usually try to keep my coefficients positive, but it's not the end of the world if you went the other way. On the other side, you'd have had a negative 2x, and you could proceed that way as well. No big deal. And then our plus 6 just comes down. I've got my variables together. I only see one x anywhere in my equation now, that 2x term. Now I want to isolate the variable term. I have a 2x plus 6. This plus 6 is added onto my variable term. I want to get it off of my variable term. I add its arithmetic inverse. I add negative 6 or subtract 6. And I do that to both sides. 2x plus 6 minus 6 just gives me 2x on the right side. And 2 minus 6 gives me negative 4 on the left. Now I've isolated the variable term. I've done that successfully. I have something that looks like number times x equals number. I want to isolate the variable itself. I have number times x. I want to multiply by the multiplicative inverse. I want to multiply by 1/2 to get rid of the factor of 2 multiplying x. And I better do that to the other side as well. 2 times x times 1/2. Well, 2 times 1/2 is 1. It just gives me 1 times x, or just x. Negative 4 times 1/2. That's a negative 4/2, or that's negative 2. So my solution is x equals negative 2. And because I just harped on it, let's go ahead and check. Is it true that 5 times 2 times negative 2 minus 1 plus 7, does that equal? When I'm doing this kind of a thing where I'm checking, I usually put a little question mark above my equal sign, kind of indicating that I'm not sure if this is true. Working to verify this. Is that 2 times negative 2 plus 3 plus 10 times negative 2? Is that true? Well, let's start chipping away at it. 2 times negative 2 is negative 4. Negative 2 plus 3 is 1. And 10 times negative 2, well, that's negative 20. If I want to add negative 20, that's the same as subtracting 20. On the left-hand side, I have negative 4 minus 1 is negative 5. Is that equal to 2 times 1, or 2 minus 20? That's negative 18. Is negative 25 plus 7 equal negative 18? Yes, that is a true statement. So I've checked, I've verified that this is indeed a correct solution, and it's the one and only solution to this equation. There were a lot of steps to solve this equation. I mean, I had to do a few steps on each side to simplify, and then I had to do one equation solving step to combine my x terms together, another one to isolate my variable term, and another one to isolate my variable itself, and then several steps to check. There were a lot of steps, but I think the overall strategy was not any more difficult than the simpler problems that we did last time. So it's the same kind of thing. We simplify, we isolate the variable term, simplify again, we isolate the variable, simplify again, and then we check. Okay, let's look at this similar problem. We have, again, just a linear equation. We only see anywhere the variable, t in this case, to the first power, but this looks really complicated, right? It looks really complicated, but it's fundamentally the same as our simpler linear equations we saw last time. The complication is just superficial. So can we simplify it? Yeah, let's start by working with each side independently. I'm actually gonna cheat this over to the right a little bit, give myself a little more room. I chose to write this 5 minus 2 times 6 plus t is 5 plus negative 2 times 6 plus t. So when I distribute, I don't mistakenly leave off a negative sign. On my left side, I have 3 times 5 plus the negative 2 distributes. I get negative 2 times 6 is negative 12, and then minus 2t. And let's continue working with the left-hand side until we get it as simple as we can. 5 plus negative 12, that's 5 minus 12, or that's negative 7, minus 2t. And now my 3 can distribute. 3 times negative 7 is negative 21. 3 times negative 2t is minus 6t. And this looks like number times variable plus number, negative 6 times t plus negative 21. This is as simple as we can get at this point. Now let's work on the right side. This one's a lot easier. I'm just going to distribute my 3. 3 times 2t gives me 6t. 3 times negative 12 gives me negative 36. So at this point, I have simplified. And I have negative 21 minus 6t equals 6t minus 36. I have number times variable plus number on both sides of the equation. This is as simple as I can get it. And now I'm going to start doing my equation solving steps. I do see that I have more than one variable term. I have t occurring in more than one place in this equation. Let me get all of my t's, all my variable terms on one side, and combine them into a single variable term. I could either subtract 6t from both sides to move this bit over to the left, but that's going to give me a negative coefficient. I'll go the other direction and add 6t to both sides. So the minus 6t plus 6t will net out to 0, but I better add 6t on the other side as well. On the left side, I have negative 21 minus 6t plus 6t. I'm adding two arithmetic inverses together. They add to 0. On the right side, be a little careful here. We might, look at this and we might try to jump the gun or something and think that like the 6t's cancel out, but they don't. They add together. 6t plus 6t is 12t. So we're doing this very carefully, step by step, so that we don't make any silly mistakes. So we get 6t plus 6t is 12t minus 36. I've now got my variable terms, my variables all combined. In other words, I look at this equation, negative 21 equals 12t minus 36. I only see t popping up one time in this whole equation. Now I want to isolate my variable term by taking that negative 36 that's kind of globbed onto the variable term and moving it to the other side. I have a minus 36. I add its arithmetic inverse plus 36. And I do that to both sides. Remember, the most important thing about equation solving steps is we do the same thing to both sides of the equation. We want to keep that balance balanced. So if I do something to one side, I got to do it to the other side so that it stays balanced. Minus 36 plus 36, that nets out to 0. I'm just left with 12t on the right. And negative 21 plus 36, or that's just 36 minus 21, that is just 15. I have now successfully isolated my variable term. My 12t, number times variable, is by itself. Now I isolate the variable itself by dividing by the coefficient of t, or by multiplying by the multiplicative inverse of the coefficient, multiplying by 1/12. And again, I better do that to the other side as well. On the right side, I can use my commutative property of multiplication and get 12 times 1/12. Well, that's a number times its multiplicative inverse. That makes 1. So I have 1t on the right side, or I just write that as t. And on the left side, 15/12. And my solution is t equals 15/12, but I see that there's a factor of 3 in the numerator and the denominator. So I might say that t equals 5/4, or I might choose to write this as 1 1/4, or as 1.25, whatever the problem calls for. Leave it as an improper fraction, write it as a mixed number, write it as a decimal. In my mind, those are all acceptable forms to write the answer. Any questions so far? And then, of course, ideally we would go back and check. We'd plug t equals 5/4 back in, go through, and show that the two sides are equal. Okay, so let's look at this one. So we have 3/4 times 4m minus 8 plus 7 equals 4 minus 2m. Let me just look. I think I'm actually going to take this one. I want this one in with these. That somehow made it out of the exercises, and that's supposed to be part of the exercises. So those will be practice problems. But we're going to work on solving this one. So again, I look at this right-hand side, 4 minus 2m, that's already in number times variable, number times m plus number. That's already good to go. That's simplified. But the left-hand side, we still have some work to do. So let's take a look at the left-hand side. Maybe I'll stick with my color coding. So just looking at the left-hand side here, because the right-hand side's already good to go. 3/4 times 4m minus 8 plus 7. I can distribute this number into that parentheses. It's a fraction, but it can distribute just fine. So I have 3/4 times 4m minus 3/4 times 8 plus 7. And I might notice 3/4 times what amounts to 4/1, or that's like 3 times 4/4. The 4's divide out, and I just get 3m, right? 3/4 times 4m. This is just 3/4 times 4 times m. But this is like 3/4 times 4/1 times m. Or that's like 3 times 4 over 4 times 1, and I see my equivalent fraction. Oh, and m there. My equivalent fractions property says I can divide out these 4s, giving me 3 over 1 times m, or 3 over 1, of course, is just 3. And I can do something similar here. The 4 in the denominator divides out the factor of 4 in the 8, leaving me with a factor of 2. 3 times 2 is 6, plus 7. And we have 3m minus 6 plus 7 is a plus 1. My left-hand side, after all of this, boils down to just 3m plus 1. My 4 minus 2m was already good to go, so nothing I need to do to the right-hand side. I can now proceed to my equation solving steps, working with 3m plus 1 equals 4 minus 2m. Okay, I now have this kind of structure, number times variable plus number on both sides. I do see that I have my variable popping up in different places, a 3m term on the left and a minus 2m term on the right. I want to start by getting my variables together, and I'll choose to do that by adding 2m to the right-hand side and to the left-hand side. Again, if you chose to subtract 3m from both sides, you'd have a negative coefficient on your m. Minorly annoying, but not that big of a deal, especially not in equations. A little more annoying in inequalities, say in MAT080, but it's not a huge deal there either. It can be dealt with. But 4 minus 2m plus 2m just gives me 4. 3m plus 2m gives me 5m plus 1. I look across my whole equation, I only see the variable in one place now, 5m. That's the only term that has a variable m in it. And now I'll continue working to isolate my variable term. My 5m has a plus 1 attached to it. I want to get rid of that plus 1. I add its additive inverse, minus 1. And I better do that to the other side as well. 5m plus 1 minus 1, that's just 5m plus 0, or just 5m. And 4 minus 1 is 3. I have now successfully isolated my variable term. My 5m is by itself, and all of the constants are on the other side. Now I want to isolate the variable itself. I want to get m by itself. It has a 5 multiplied onto it. I either think of dividing by 5 or multiplying by the multiplicative inverse, 1/5. And I better do that to the other side as well. 5 times 1/5 is 1. 1m is just m. And on the right-hand side, 3 times 1/5, we can just write that as 3/5. So that is our one and only solution. And again, ideally, we would go back, we would plug this in, we would check our work. But for time considerations, we're not going to do that here. Any questions so far? Okay, so I have 3 equations here for exercises. Just like the ones above, these look really complicated. They look a little scary. But most of the scariness, or really all of the scariness, I suppose, is just superficial. Once we take the left-hand side and the right-hand side individually, go through the steps to simplify them down, it's no more theoretically complicated than any other linear equation. It's just that, in this initial state, it looks more complicated. So work through these 3 problems. These will take a little more time, so we'll probably take about, let's take about 9 minutes, maybe 3 minutes each. I think that'll be a good amount of time. If you don't get finished with all 3 of them, don't worry about it. It's not, that big of a deal. But I'm trying to balance, being able to make it through all the material and get to the review with giving you enough time to get a good shot at these. Maybe don't worry about checking your work unless you get through all three and then cycle back and check. But we'll take about 9 minutes. And as usual, a few minutes in, I'll start writing a couple of the first steps out for each of these. So we'll take about 9 minutes and we'll come back and go through the solutions quickly. Okay, it's been about 9 minutes, so let's take a look at these. Again, if you didn't completely finish everything or if you didn't have time to check your answers, not a big deal. There are a lot of just simplification steps in each of these problems. So in the first one here, we are going to start by simplifying both sides. So 2 times 5x plus 3, we can distribute through, we get 10x plus 6 minus 1, or 10x plus 5 on the left. And then we get 8x minus 3 on the right after a similar kind of simplification. So now we're looking at 10x plus 5 equals 8x minus 3, and that is in the standard form, ax plus b equals cx plus d. We have number times x plus number on both sides. We now want to work towards isolating our variable term. So the first thing we got to do is get the variable terms together. We only want to see one variable term in the entire equation. And I'll choose to do that by subtracting 8x from both sides. That gets rid of the 8x on the right side. 8x minus 8x gives me 0 and then minus 3. So my right side is just negative 3. And on the left side, 10x minus 8x is 2x, and the plus 5 just kind of comes along. Now I look at 2x plus 5 equals negative 3. I only see my variable once there. There's only one variable term, the 2x. So now I'll isolate that variable term by saying, okay, I have a 2x plus 5. I want to add the additive inverse. I want to add negative 5 onto that, or subtract 5. And I want to do that to both sides. So 2x plus 5 minus 5 gives me just 2x. Negative 3 minus 5 gives me negative 8. 2x equals negative 8. And now I've successfully isolated my variable term. I have the number times x by itself. And then lastly, I want to isolate the variable itself. I have number times x, 2 times x. I want to multiply by the multiplicative inverse of 2, 1/2, so that 2 times 1/2 is 1. I just get 1x, or just x, equals negative 8 times 1/2, or negative 8 halves. X is just negative 4. And again, we could plug in to the original equation, check the both sides balance. So my next one, it's a little jumbled with the third one here. There we go. My second problem here, I was trying to fit everything on the screen and I still ended up running out of room. But the first thing I want to do here is rewrite things. And I'm going to choose to rewrite this minus 4 times stuff as plus negative 4 times stuff, so I don't forget to distribute the negative. The negative 4 distributes through. Negative 4 times 3 is negative 12. Negative 4 times 2t is minus 8t. 2 plus negative 12 gives me negative 10. And then distributing my 5 into both of these two terms, then negative 10 and the minus 8t gives me a negative 50 minus 40t. Doing something similar on the right side, distributing my 5 into my binomial, 5 times 8t minus 5 times 10, or that's 5 times 8 is 40, t minus 50. And I can set these equal to one another. Now I have, well, what do I have? I have negative 50 minus 40t equals 40t minus 50. That is in standard form, number times variable plus number on both sides. I do see that I have my variable in a couple of different places. I have two different variable terms. Let me combine them under a single variable term. I'll choose to add 40t to both sides. This gives me just negative 50 left over on the left side, and 40t plus 40t is 80t on the right side, minus 50. I'm working toward isolating my variable term, this 80t. This 80t has a minus 50 still attached to it. So let me add the additive inverse of negative 50, which is positive 50, to both sides. 80t minus 50 plus 50 just gives me 80t. And actually, minus 50 plus 50 gives me 0 on the left-hand side. So I have 80 times t equals 0. We can either just by inspection see that t has to be 0. Or I could say, well, 80t times the multiplicative inverse, 1 over 80, equals 0 times 1 over 80, but 0 times 1 over 80 is just 0, so I have t equals 0. And again, I could plug back in and show that this is indeed a solution. As kind of an aside, one thing I might have noticed here is I have a 5 multiplying everything on both sides. If I see a trick, I can try it. It's a valid equation solving step to multiply both sides by 1/5. This doesn't exactly follow our strategy exactly as it's laid out, but if I were to multiply by 1/5 first, I'd have 1/5 times 5 times a bunch of stuff. That would just leave me with 2 minus 4 times 3 plus 2t on the left. And 1/5 times 5 times some stuff gives me just that stuff, 8t minus 10. And I could simplify this and then solve. I'd be able to do this in fewer steps. It would be a little bit simpler. I wouldn't have as big of numbers to work with. It turned out not to be a huge deal here. The numbers weren't, absurdly large. They weren't super difficult to work with, and ending up with a 0 made it a little bit easier as well. But I could have divided by 5 at the very beginning and made things even a little bit simpler. And then for the third problem, we have 2/3 times 6m minus 9 plus 5. That's on the left side. That can definitely be simplified. The right side, 4 minus 5m, that's already as simple as we can get it, so we'll leave the right side alone and work on the left side. So distributing my 2/3, I have 2/3 times 6 times m minus 2/3 times 9 plus 5. Just looking at the left side here. 2/3 times 6, well, the 3 in the denominator divides out one of the factor of 3 and the 6, leaving me with a factor of 2 multiplied by 2 gives me 4. So 4m. And similarly with the 2/3 times 9, 2/3 of 9 is 6, or you could think of the factor of 3 in the denominator dividing out one of the factors of 3 in the 9, leaving me with 2 times 3 or 6. And then plus 5, it just comes down. And then finally, I have 4m minus 6 plus 5 is 4m minus 1. So now I'm looking at my simplified left-hand side, 4m minus 1. That's number times variable plus number. And something similar on the right side, 4 minus 5m, also number times variable plus number. I've got my two sides as simple as I can get them. And now I start applying my equation solving steps. I note that I have two variable terms, a 4m on the left and a minus 5m on the right. Let me start by trying to get those under one term. And I guess I'll choose to add 5m to both sides. On the right, I have 4 minus 5m plus 5m. That's just 4. On the left, I have 4m plus 5m. That is 9m minus 1. I have now got my variable terms combined together. Let's work on isolating this variable term. We do that by adding 1 to both sides. I am speeding up here a little bit, so if you have any questions, definitely ask, slow me down. But since I'm presuming that you've worked through most of this already, I'm going a little quicker than maybe I normally would. But I have 9m equals 5. I've isolated the variable term. I now want to isolate the variable, multiplying both sides by 1/9. And I get m equals 5/9. And again, I would ideally go back, plug this in, double check everything. We're not going to do that just for time's sake. But are there any questions on any of these? Okay. So let's jump down to 8.4 then. Solving equations with fractions or decimal coefficients. We did see an equation with fractions here, and one that we did as an example. But notice that it kind of worked out really nicely, right? Distributing this fraction, it ended up going away. The 4 in the denominator worked nicely with the 4 and the 8 in the numerator, or the 3 in the denominator worked nicely with the 6 and the 9 in the numerator, and the denominators went away. The fractions went away. I could apply my equation solving steps here. I could say this is number times x plus number equals, well, number times x plus number, but it's just kind of 0 times x plus 5/3 on the right. I could isolate my variable term, my 1/3 x, by, say, subtracting 2/3 from both sides. 5/3 minus 2/3. They have 1/3 x equals 3/3, or 1/3 x equals 1. And now what I want to do, I have my variable term isolated. I have a coefficient of 1/3 on my x. To get rid of that coefficient of 1/3, I want to multiply by the multiplicative inverse. 1/3, its multiplicative inverse, I flip the fraction. It's 3/1, or we'd usually just write that as 3. I want to multiply by 3 on the left and do the same on the right. 1/3 times 3 is 1. 1 times x is x. And 1 times 3 is 3. I can apply my equation solving steps. That's not, in theory, a problem. However, I mean, moving these fractions around gets a little bit tedious. These were even pretty nice fractions. Everything was already over a common denominator. They were really easy to work with. Remember up here, I said we might have recognized a shortcut that we could multiply both sides of the equation by a number at the very beginning to make the following simplifications and equation solving steps simpler. That's something we might want to do, especially when we have fractions or decimals as coefficients. In other words, I could take 1/3 x plus 2/3 equals 5/3. I can multiply both sides by, for instance, 3. I would have 3 times 1/3 x plus 2/3 equals 3 times 5/3. I do have to be really careful if I multiply by a number like this when my equation's still, kind of complicated. I need to make sure that I multiply the entire side by that number. So it's 3 times the whole parentheses, 1/3 x plus 2/3. It seems like I've made things more problematic for myself because now I need to distribute. And it seems like I've made things more complicated, but I noticed that 3 times 1/3 x just gives me x. And I noticed that 3 times 2/3 just gives me 2. And 3 times 5/3 just gives me 5. That's a heck of a lot nicer equation to solve than even this pretty nice equation up here with fractions. And the fractions could have been a lot worse. I just subtract 2 from both sides, x equals 3, and there is my solution. So we're introducing kind of a new step into our mix here. If we have fractions, or I mean, decimals are kind of the same as fractions, so this would apply to decimals too. But if I have fractions popping up as coefficients, then I want to do what's called clearing the fractions. I want to multiply both sides of my equation at the beginning of everything. I want to multiply both sides by a number that will clear all the fractions, that will get rid of all the denominators. And what I'll do is I'll multiply by the LCD of the fractions. Now here we had a common denominator, 3, for everything. So the lowest common denominator, of course, is going to be 3, the existing common denominator. But our strategy is the same as it was before, with the exception that we'll do step 0, we'll call it, where we clear fractions or decimals first. All right, let's look at an example. So let's solve 3/2 t minus 2/3 equals t plus 5/3. If I look at my denominators, I have 2 and 3. Obviously, the prime factorizations are 2 and 3. And my LCD, my lowest common denominator, is 2 times 3, or 6. So this is an LCD that's not super hard to find. My LCD is 6. If I was, say, adding fractions together, if I wanted to add like or subtract 3/2 minus 2/3, I would make each of my fractions have a denominator of 6. But here I'm trying to get rid of the fractions. I'm going to multiply both sides of the equation by 6. One thing I really want to be careful of, and this is a side note, if I had 3/2 minus 2/3, this expression I can't just like take this expression and multiply it by 6 and get rid of the fractions. I can't just say 6 over 2 is 3 times 3 is 9 minus 6 over 3 is 2 times 2 is 4, and that this is 5. Clearly 3/2 minus 2/3 is not 5, right? That's pretty clear. I can't just do this. So if I'm doing arithmetic with fractions, I can't just go around multiplying by some number. I mean, I suppose maybe I could multiply by 6 over 6, but now we're getting pretty complicated. Why can I get away with that here? Because I have expression equals expression. I can't just arbitrarily take an expression, multiply it by a number, and have it be the same expression. But if I have an equation, I can multiply both sides of the equation by a number, and the result will be an equivalent equation. It'll have the same solutions. So I could choose to multiply 6 times 3/2 t minus 2/3. I can choose to multiply by 6 on the left if I also multiply by 6 on the right. Right? Another way of thinking of it is if I have a basket of goods and I have a certain amount of rice or whatever in this basket, if I put 6 times the amount of rice in that basket, I have a lot more rice. Like that's not the same expression. That's not the same amount of rice I had before. But if I say this, basket of rice balances with this basket of apples, and then I put 6 times as much rice in here and 6 times as much apples in here, it still balances. There's more rice and apples, but it still balances. An equation is a statement that says things balance. An expression is a statement that says, in some sense, like how much of the thing there is. So these are still equal, even though each side, might look a little bit different. I distribute my 6 into the 3/2. 6 times 3 is 18, over 2 is 9. 9t minus 6 times 2/3. We could think of 2/3 of 6 being 4, for instance. And I distribute my 6 over here as well. 6t plus 6 times 5 over 3, or 6 times 5 is 30, over 3 is 10. 6t plus 10. By multiplying by the LCD of all my fractions, I end up with an equation in standard form where all of my coefficients are integers. So I don't have any fractions left over. Again, is this step absolutely necessary? Well, no, but it means I don't have to deal with simplifying a whole bunch of fractions on every step, right? I kind of get rid of my fractions, and all my intermediate steps now will be in integers. Maybe I have a fraction at the end. I could always end up with a fraction at the end like I did here. That even came from, a problem where everything worked out pretty nicely and I had integers in the intermediate steps, but ended up with a fraction at the end. That might happen, but I don't have to deal with fractions every single step, right? That makes the simplifications easier. That makes the equation solving steps easier to deal with. So now I just go ahead and solve this like I've been solving my equations. I see my equation has 2 variable terms. variable in two different places. Let me get those together. I'll choose to subtract 6t off both sides. 9t minus 6t is 3t minus 4. 6t minus 6t is 0. Leave me with just 10 on the right. I've got my variable terms together. I look at my full equation, 3t minus 4 equals 10. I only see t popping up in one place. Let me work on isolating that variable term. I add 4 to both sides. 3t equals 14. And now I have 3 times t equals 14. Divide both sides by 3. T equals 14 thirds, and that's my answer. So I did end up with a fraction at the very end, but every one of these intermediate steps only was dealing with integer coefficients. A lot easier for me to deal with. The downside is that sometimes the LCD can be kind of big. So sometimes we have bigger integers to deal with rather than like smaller fractions. So there's a little bit of a trade-off there, but I think it's almost always worth it. So clear the fractions, proceed with all of the equation solving in the integers, and then maybe recover a fraction at the end. But it makes our intermediate steps a lot simpler. Any questions on that? Okay, so do this one problem as an exercise. We'll take maybe 3 minutes or so to do this one. Start by finding an LCD for the 3 fractions that occur in this problem. Multiply by that LCD. Be really careful when you multiply to multiply against everything on the one side and everything on the other side, distribute properly and all of that, and then get a solution. So we'll take about 3 minutes, and as usual, about 60 or 90 seconds in, I will jot a couple notes down, and then in 3 minutes, we'll talk about the answer. Okay, it's about 3 minutes, so let's take a look at the answer. So the LCD ended up being 12, the lowest common denominator between the denominator 6, 4, and 3. 6 factors into 2 times 3, 4 2 times 2, and 3 just 3. So we need 2 factors of 2 and 1 of 3 to make the LCD. That's 12. We multiply both sides by 12. Be careful to distribute carefully to everything on both sides. 12 times 5 over 6. Well, 12 over 6 is 2. 2 times 5 is 10. So that's 10x. And then plus 9 equals 24x minus 20. So here I need to get my x's on the same side. I have two variable terms. I need to combine them under one variable term. And I'll subtract 10x from both sides. So on the left, 10x minus 10x is 0, and I'm just left with a 9. And on the right, 24x minus 10x is 14x, and the minus 20 comes down. I now have one variable term across my whole equation. I only see the x popping up once. So I want to isolate the variable term by adding 20. I have the minus 20. I want to add the additive inverse, positive 20, to get rid of that. So 14x minus 20 plus 20 is just 14x. And I better do that to the other side as well. So adding 20 to the other side gives me 29. And then lastly, I divide both sides by 14, or I can think of it as multiplying by the multiplicative inverse, 1/14. So on the right, that leaves me with just 1x, or just x, and on the left, 29 over 14. And that is my answer. Any questions on that one? Okay. I think I'm going to make a note about this one, but not fully solve it, just for time considerations. For a problem like this, we might say, okay, do we want to multiply both sides by 15 and clear fractions? And again, that would work. We could follow the strategy step by step as it's written, but we might notice here that actually this problem, these fractions actually work pretty nicely with the problem as is. If I just distribute, 1/5 is going to work really nicely with the 5x and the minus 10, leaving me with just 1/5 times 5x is x, minus 10/5 or minus 2. And on the other side, 1/3 times 6x is 2x, and 1/3 times 9 is plus 3. If I see a good reason to deviate from my problem-solving strategy, so long as I'm doing legal steps, legitimate equation solving steps or something like that, I can do that, right? I would much rather work with this than if I multiplied both sides by 15. I would get what? I'd end up multiplying by 3 in this parentheses, so I get 15x minus 30, and by 5 in this parentheses equals 30x plus 45. I'd much rather deal with these numbers and not these much bigger numbers. Again, it's still a legitimate strategy. We could still go through and solve this, and we would get the exact same solution as over here, just a little bit more tedious and complicated. So if I see a good reason to deviate from my problem-solving strategy, if I see a little shortcut I could take, I'm fine to do that, as long as I just make sure that I'm applying proper technique, that I'm still using valid equation solving steps and so on. And this one I think I'll skip over as well. This is just a different way of writing 1/8 times 2x plus 3 and 1/2 times 5x plus 1. We'll skip over that one because I want to get down to the exercises after this problem. Okay, so how do we handle decimals? Well, I know that decimals are basically fractions, right? 1.7 is like 17 over 10, 3.2 like 32 over 10, right? I see that I have one decimal place here, 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 and here. One decimal place equates to kind of one factor of 10 in the denominator. Well, if I multiply both sides of my equation by 10, what do I get? I'm essentially clearing this fraction. As long as I multiply both sides by 10, I'm good. I distribute. What is 10 times 1.7? That just bumps this decimal point 1 to the right. That is 17. Does the same thing to 3.2, bumps the decimal point 1 to the right, making 32. And similarly over here, I distribute my factor of 10. 10 times 4.8 bumps the decimal point 1 to the right, making a 48x, and same to the 9.1, making 91. These are bigger numbers. That's the price I pay for doing this. But the benefit is I don't have to deal with decimals. I don't have to deal with fractions. So I get to deal with integers instead of fractions or decimals, but the price I pay is that the numbers I have to deal with are a bit bigger. But I notice now that I'm in this kind of standard form, number times x plus number on both sides of the equal sign, and I can proceed with my equation solving steps. I see I have two variable terms, the 17x and the 48x. Let me get them on one side under a single variable term. And I suppose I will subtract 17x from both sides. Right, adding the additive inverse of 17x to get rid of it on the left side. That makes a 0 minus 32. On the right side, 48x minus 17x is, I think, 31x, right? 48 minus 17 is like 48 minus 10 minus 7. We could think of it that way. So 38 minus 7 or 31 plus 91. Now I see that across my entire equation, I only have the variable occurring once. I have that single variable term 31x. Let me work on isolating the variable term. I need to get rid of this plus 91 that's attached onto it. I do that by subtracting 91, and I better do that to the other side as well, so my equation stays balanced. On the right side, I have 31x plus 91 minus 91. Those bits go away. On the left side, I have negative 32 minus 91. That is negative of 91 plus 32. Well, 91 plus 30 is going to be what? 121 plus another 2 is 123. And now I have number times x equals number. It's not the nicest number in the world, but it's what it is. I multiply by the multiplicative inverse of the coefficient of x, multiply by 1 over 31. And let me do that on both sides. And I end up with x equals negative 123 over 31. I look at this and I notice that I think 31 is a prime number, right? It doesn't seem like it's gonna, it's not even. It's not gonna be divisible by 3 because 3 plus 1 is 4, not divisible by 3. Clearly not 5. 7 times 4 is 28, so 31 over 7 would have a remainder of 3, so not divisible by 7, and it can't be divisible by anything bigger than 7 without being divisible by something less than 7 as well. So I've got up to the square root. 7 squared is 49, bigger than 31, so I know the 31 is prime. And so my only other question is 123 divisible by 31? Is 123 equal number times 31? Well, 31 times 4 would be like 124, right? It'd be like 30 times 4 plus 1 times 4. And it doesn't divide nicely, and that's way too close for anything else. 31 times 3 or something, or 5 is not going to be 123. So this is the best we can do. Okay. Not the prettiest fraction ever, but it is what it is. We could maybe write it as a mixed number, right? We might be able to write it as a decimal approximation, maybe, rounded to the 10th place or something. But but that's all we can do. We can't simplify it any further as a fraction. Okay, let's take a look at two exercises here. So work through these two problems. This one should look quite similar to the last one. This one might be a little different. So think about how we could adapt our strategy from the last one, or maybe the more like the tactics, the, you know, play by play. How can we adapt that uh, to this problem that looks a little bit different? Ask yourself, how is this one different than the previous one, and how can we adapt our strategy to that? Maybe take about, let's say about 6 minutes to work through these two, and we'll come back and discuss. And as usual, I'll write up a couple of hints along the way. Okay, it's been about 6 minutes, so let's take a look at this one, or these two. The first one, we see that we have one decimal place here, one there, and one there. So by multiplying by one factor of 10, that should clear our decimals. As I multiply it by 10 on both sides, and I'm very careful to multiply by the entire side. 0.2 times 2 minus 3x minus 1.4. That whole thing multiplied by 10. And on the right side, 10 times 2.7 times x minus 1. On the right side, I'll use my associative property and regroup this as 10 times 2.7 times x minus 1, or 10 times 2.7 is just 27. On my left-hand side, I'll distribute. I have one bit minus another bit. I'll distribute my factor of 10 into that. So 10 times 0.2 times 2 minus 3x minus 10 times 1.4. The 10 times 1.4 just bumps the decimal point 1 to the right, making 14. And again, I'll reassociate the 10 with the 0.2. 10 times 0.2 bumps the decimal point 1 to the right, making a 2. So I'm left with 2 times 2 minus 3x minus 14. And that equals 27 times x minus 1. And at this point, I will distribute, simplify, and get down to a linear equation in standard form. Then I work on isolating my variable term by adding 6x to both sides, getting my 33x by itself by adding 27 to both sides. That isolates my variable term, and then I divide through by 33, or you can think of it as multiplying by 1 over 33. That gets my solution. The next problem, any questions on that one? The next problem had a little bit of a wrench thrown in it because here I do have one decimal place here, but I also have a term with 0 decimal places, and I also importantly have two terms that have 2 decimal places. If I want to clear all of my decimals, I have to multiply by 100 because these two terms, the 0.25x and the 0.37x, need their decimal point moved 2 places to the right to clear the decimal. If I only multiplied by 10 here, I would have a minus 1 there and a plus 40. I don't have decimals there, but I still have a 3.7x and a 2.5x. So multiplying by 1 power of 10 not enough. Need to multiply by 2 powers of 10. We could think of this in terms of fractions as well. 0.25 is like 25 over 100, 25 100ths. 0.37 is like 37 over 100. So, and 0.1 is 1 over 10. My common denominator, my lowest common denominator is clearly 100. Could think of it that way as well. Multiplying by 100 on the left side and on the right side, distributing this minus 0.1 is minus 0.10, bumping that decimal point 2 to the right, gives me a minus 10. So 25x minus 10. And 100 times 0.37 is 37x. And 4 times 100 is 400. It's not a bad idea, I don't think, to write out the decimal like 4.00 and move the decimal point 2 to the right. When you're multiplying numbers that are of different sizes to start with, like 0.1, 1/10 is kind of a small number relative to, say, 4. It would be easy to make just an arithmetic flub and end up with this being like 40 or something like that instead of 400, just forgetting one of your zeros. But writing it as 4.00 and moving the decimal point 2 places like we did everywhere else, or writing the 0.1 is 0.10 and moving 2 decimal places. We're moving 2 decimal places everywhere. I think it makes it a little more clear. And then again, we just do our equation solving steps. The numbers are a little bigger here, but not unmanageable. And when I get down to 410 or negative 410 over 12, I noticed the numerator and denominator are even numbers, so I can divide out a factor of 2. 410 is 2 times 205, and 12 is 2 times 6. Can I simplify this fraction any further? Well, 6 has factors of 2 and 3. 205 is not an even number, so 2 is not a factor of it. Is 3 a factor of it? Well, 5 plus 2 is 7, not divisible by 3. So 205 is not divisible by 3. We can't simplify any further. Any questions on this? Okay. So I think what I would like to do in our last 13 minutes or so, I put together just a quick review of chapter 8, just, some practice problems. So I've split this into basically 3 problem sets of 2, 2, and 3 problems. We might not get to the last one, but the last one is really kind of reviewing the more recent stuff that we have just reviewed with a bunch of exercises. But let's try to get through these first two sets. So I'll actually tighten these up a little bit so that maybe we can get them all on here at once. I think that will work. So take a look at these 4 problems. Try to work through these 2 in maybe about 4 minutes. These should be a little more straightforward. And we'll discuss them quickly. I'll write up the solutions, discuss them quickly, and then we'll go through the last 2 in the time that remains. Okay, it's right around 3 minutes. Let's just quickly discuss these 2. And then we can move on to the next 2. So for this one, we want to start by simplifying each side. And I did it kind of in one step here because we're getting a little more used to doing these simplifications, we distribute the 5 into the x minus 1, making 5x minus 5, then minus 4x equals, and we can distribute these 3's on the right-hand side. 3 times x plus 3 times 3 is 9, 3x plus 9. We want to be careful here. This minus 3, when we distribute it, it's kind of like a plus negative 3. So we want to distribute it to the x as a minus 3x and distribute it to the 1 as negative 3 times negative 1 is a plus 3. So be a little careful with that sign. Simplifying the left-hand side, 5x minus 4x is x minus 5. And on the right-hand side, 3x minus 3x, they go away. 9 plus 3 is 12. So I have x minus 5 equals 12. And I can solve this with one equation solving step, just adding 5 to both sides. 12 plus 5 is 17, x equals 17. And if I wanted to, I could go back and check that. And my next equation is actually quite simple to solve. It's already in standard form. So I want to get my x's together to start working on isolating the variable term. And it turns out when I do that, I subtract 15x off both sides. On the right side, 16x minus 15x is just x. And on the left side, 7. I just end up with my solution coming right out, x equals 7. Okay, so start working on these two, or you might have already started on these two. And we'll take about, let's say, 4 minutes for these and discuss in the last couple minutes of class today. Okay, so in the last minute or so that we have here, just quickly discussing these two problems. In the first problem, we distribute and we simplify, and we end up with 14x plus 27 on the left equals 12x minus 22 on the right. We have our equation in standard form, ax plus b on both sides. So we start by getting our x terms together by subtracting, say, 12x from both sides. If you did it the other way, as always, that's okay too. 14x minus 12x gives me 2x on the left plus 27 equals just the negative 22 on the right. Now I want to get my 2x term by itself. It has a plus 27 attached to it, so I subtract 27 from both sides, leaving me with 2x equals negative 49, negative 22 minus 27. And then lastly, I have 2 times x. I want to multiply by 1/2. So I have 2 times 1/2 is 1, 1 times x is x. And I better do that on the right side as well. Negative 49 times 1/2 is just negative 49 halves. And that's our answer. And again, we could write that as a mixed number or a decimal if we wanted to, but I'll just leave it this way. And our problem down here, it's useful to see that we have a factor of 3 on both sides. So actually by multiplying by 1/3 before I do anything else, I can clear that factor of 3. I have 1/3 times 3 times the square brackets equals 1/3 times 3 times the parentheses, and that makes things a lot more manageable. I, again, just distribute, simplify, I end up with 14 plus 8t equals 6t minus 10. And I do my equation solving steps from there. Subtract 6t off both sides to get 2t plus 14 equals negative 10. That gets me down to one variable term. I subtract my 14 from both sides to get my variable term by itself. 2t equals negative 24, and then I multiply by 1/2 to get t equals negative 24 over 2, or t equals negative 12 as my answer. Let me stop the recording.